for talks entitled Geochemical Renaissance Opportunities for Exploration Programs.
All right, well, thank you very much, and thank you all for coming. It's a bit of a packed room. I'm sorry, this is finals week here at School of Mines, so all the rooms around in the normal room are full of students taking finals. Have to squeeze all of a week's worth of activity in the classes that happen here into 4 days for finals, so they run all day and into the evening. So a little bit packed for those of you that are online. You have the benefit of being able to breathe. Everyone here is a bit snug. Okay, so I have to give credit. You know, anytime you talk about a general topic, you're standing on the shoulders of a lot of other people that have worked in the fields, co-workers, and I don't know if any of you remember Lloyd James. He was a mentor of mine in my early years. Bill Coker, Graham Kloss, you know, people that we don't see here quite as often. And and I've also worked around some incredibly capable geochemists in my career. So my comments aren't necessarily work that I've done, but where we are within the industry. Wow. So as you heard, we have a professional master's degree program, and that's my primary role here at School of Mines, is to coordinate and recruit for that. It's a non-thesis program where the students need to take a minimum of 10 courses that include economic geology, exploration geochem, exploration geophysics, structural geology, a pretty wide range of choices that they have. And so we have between 20 and 25 students in the program. There's a few of them here tonight. And we get people in from between 5 and 10 different countries at a given time, some that are just coming through from their bachelor's and others that have worked in the industry for a good period of time and bring their own level of experience to the program. And within that, I guess we have about 5 of our current students that are sponsored by their companies. And so that's sort of where we'd like to be at that level of 20 to 25. It's quite manageable. And all the economic geology professors in the department help teach the courses. So a geochemical renaissance is the topic of tonight. And so I hope to present what's current, what's exciting, where are we moving to, where are the opportunities that make this a great time to be a geochemist and spend time with this periodic table. So we're gaining all the time new information, new understanding of ore deposits, alteration, and geochemical footprints. We have some new instrumentation that's come on board in both the geochemical laboratories as well as the mineralogical capabilities. We've got a lot of advancement happening in trace element isotopic applications. And mineral chemistry is an entire field these days of research on a global basis. We're doing a lot of work, as many of you probably know, around spectromineralogy and logging capabilities, and there's a crossover of what minerals are present, but also what's their mineral chemistry and how does that tie to the geochemistry of the system and the alteration. Fortunately, we've had some great software upgrades in the last few years that are making our world a lot easier to work with. And of course, as we get more and more data, we're pushed to this point that the smartest among us can't manage all that data without some support. And so machine learning is coming in fast and furious into the geochemical world. I'll talk a little bit about that and some innovation opportunities. So the most obvious thing that's brought geochemistry alive recently is our new generation of instruments that have moved from research category into the commercial labs. So we have a new generation of ICP-MS instruments. We're now to the point that we're below crustal abundance for a lot of the pathfinders that we like. And so with that, we can go back and revisit selective extractions that kind of got parked in the 1970s and 80s, because we can now see low enough that we're seeing new patterns, new capabilities. We can revisit isotopic ratios. We're just now beginning to revisit hydrogeochemistry applications, where before we really, spent maybe 70% of our data, maybe even more, was below detection limit. That's not the case anymore. And so we're just beginning to do some of that, readdressing those. There's a new generation of selective ion electrode instruments out there. It's actually not too new anymore. So fluorine, chlorine, bromine, and iodine, they can be great companions. They're a part of the enzyme leach package, and some of that was valid. And so we can go back to these in cases where it's appropriate. Of course, with laser ablation, we have not just ICP-MS anymore, but MS-MS, where we can really push the detection limits down. Paired with EMP, then we've got a large set of new data, and we're learning more from that every day. I won't spend a lot of time on that because that's an entire topic. Xiaoshen Cheng here in the department focuses on that, and he gives entire courses and many lectures on that particular topic. I couldn't begin to do it justice anymore. And when we're looking at mineralogy, then all of our mineral chemistry can push into new levels of sensitivity and mineral mapping with all these new instruments. And of course, there's also more and more that we can do with field instrumentation. Any of you that love watching the Mars rovers know that JPL has been doing amazing work making small instruments and putting them up on Mars, and that's the precursor to things that we'll probably be able to use ourselves in the future. So start out by readdressing sample grain size for stream sediments, soils, and tills. And so what you see here on the diagram, this is a diagram that I think Owen Lavin put together at one stage. And so, we've always worked with -80 mesh as the world standard. -80 mesh sits right in, oops, myself here. My little button's not working. Sits in here, and it's designed for simplicity. If you're working at a geochem lab and you need to clean out a sieve, -80 mesh happens to be really easy to do. It's fast, it's quick. So it has become the industry standard with no science behind it. So that means we're combining silts, clay, fine sands up to the middle of fine sand in a given sample. And it's a very logical thing to do, and it's been the industry standard for years. But if this is an example of two samples here, one on the left and one on the right, we might have 80% sand grains in the one on the left, and maybe only 40% sand grains on the one on the right. So intuitively, that if the majority of the response is in the finer grain particles, you can immediately say that when we're sieving at -80 mesh, we're mixing some samples that are diluted a lot with sand and some that are diluted less. And so we get ratty, noisy responses. And much of our noise in geochem surveys is a result of mixing these grain sizes. So we've always known that if we go to a finer fraction, we get higher concentrations, sometimes 20 or 30%. And so some people will go to a -200 mesh sample. It's slower, harder. The lab calls you up and says they don't have enough material. But generally, the finer fraction is more highly charged. And so this is an example here again of two samples, one shown in the blue, one shown in the red, where again, you see this mixture. And this is the reason that we don't get consistency when we're doing soils work. So Phil Allen actually was a part of the La Colosa discovery in Colombia, and they did a stream sediment survey using a -200 mesh right there in the field because most of the drainages are wet. You could do a wet sieve. The rest of the world where you can't do a wet sieve is just not practical to go to a -200. but it's a similar concept. You get the concentration ranges up, give yourself a better chance. And so, you know, a nice discovery that came out of that program. The Geological Survey of Canada has done till sampling, where they always have collected a indicator mineral, and then they've always gone with a finer fraction of the till as a part of their routine programs. And again, it takes collecting a larger sample can be difficult, but it has been their protocol for years. Kurt Kaiser and his students at Queen's University developed a method to isolate just the clays. So when we're talking about the clays, we're talking about something in the less than, in his case, less than 10 micron range. And that was because they were looking for isotopic signatures, and they needed every chance they could get. They needed to get those low detection limits. So they put the sample in with an ultrasonic wand, disaggregate the sample the best they could, then take the water from that, centrifuge it, and then they had a very nice clay sample, and they started to get some nice work on isotopic signatures in soils from that. And so that's a bit of the standard that's been at Queen's Isotopic Lab for some time. So that method was replicated. Two of his students went to Vancouver. One of them went to work for Acme, which is now BD, and another one went to work for ALS, and they replicated that method. So both of those labs have had a fine-grained, ultrafine soil method based something like that. It tended to suffer from some quality control problems, and I don't really know enough behind the scenes to know why. So the method's still out there, but it's not utilized routinely. More recently, Ryan Noble in Perth with CSIRO tested working on some fine fraction work in Western Australia. He was very pleased with the results from that, and so he's partnered as a CSIRO partnership with a company called Lab West. They have a very small lab in Perth, and they do a method which is somewhat like the Queen's method, a little bit different. Again, producing a relatively small sample that's then analyzed for multi-element work. So you can see where I'm going, that there's a fair number of different angles on going for a fine fraction, which has been difficult in the past. And so historically, Normandy and Newmont geochemists have used the fine fraction for both legwork and soil regolith samples, and just recently have agreed to have this method published. So Simon Marshall gave a talk about some of their work at the SEG meeting here in Denver, and a few of us are working on a paper, Owen Lavin and a few of us are working on a paper that should come out soon, we hope, that will also discuss the method. And so it comes off the heels of Bill Griffin, who was a metallurgist who Normandy hired to do in-house stream sediment development work. Nigel Radford in Australia, Owen, and these guys have 20 years of development of an in-house procedure, which they called BLEG, but it doesn't actually bear too much of a resemblance to the BLEG method that you would see at a commercial lab. So this is one of the discoveries that came out of it. This is actually pretty old now, but was not well published. So this is the Bateau Pigeot copper gold porphyry. And the goal of that the geologists had was to go around the islands, skirt around the outside, go up the drainages far enough to get well away from any influence from the coast and collect a sample. So the initial sample was right here, then they came back down and they went around all of the islands in the area. So the discovery site was this sample at 7.4 ppb. If you were to go there and do a conventional stream sediment sample at a -80 mesh, you wouldn't pick anything up. And so they were also doing a -80 mesh stream sed program. And in the follow-up programs, they did heavy mineral concentrates, BLEGs, stream seds, and they didn't pick it up with a -80 until they were at this site here, which you can see is very close to the current pit. And the BLEG value there was pretty high. This site, they picked up in the -80 a number of pathfinders as well as gold. And so you can kind of see that the consistency as they worked up the drainage. Subsequent follow-up, which is something that Newmont does routinely on these big BLEG surveys, looks like this. So these are catchment basins, and you can see that the entire area has got quite a nice response after many follow-up surveys that occurred. So on these surveys of enriching the sample by going to a fine fraction, there's a few other processes that they put behind it. And the threshold will be somewhere around 2 ppb even with that. So you're still looking at very low concentrations, but it winds up being a great screening tool. And so many years, that was the method of choice for early pass stream sediment work that was done in the company. And they all would send their samples from all around the world to Bill Griffin, and he processed them all manually himself. He didn't want anybody else messing up his method. This is another one which we've been given permission to publish. And this is a different environment, which is why I threw it in. This is in Argentina, very hyper arid, low relief. So the drainages are not well developed, and there's also ash dilution in the drainages. But you can see again, a number of the sample sites are shown in the black dots. And so you have a composite, quite large area that outlines this project. So the challenge of exploring through cover is one that everyone's been working on quite a bit. In this case, this is put together for Western Australia, which is what we're going to talk about for just a few minutes. But it applies to other areas in some ways. In this case, you have an in situ regolith and then perhaps transported cover. And we're asking that the ions from some sort of buried mineralization are going to find their way up, get transported. So first we got to have them down here to look at, then we've got to transport them, and then we've got to find somewhere for them to be trapped at the surface. So Ravi Anand participated in some Amira programs. Ravi's retired now, but he worked for CSIRO. He's a fantastic geochemist and regolith expert. And so he decided he was going to do some pit experiments. He gave a talk on his work at the SEG in Keystone in, when would that have been, 2018, I think. And so he dug these pits, 1.5 meters deep, I think they were. He put some right at the CSIRO offices. They also dug a series of them at the Boddington site where they knew they had gold mineralization. So this is one of his pit experiments. So they ran 2 lines and they put basically some plastic trays in the bottom of them. Some of the trays had drainage holes so that any rainfall would go down through, not get captured in the tray and go on below. Some of them did not have holes. They put gold ore in these trays. They put a VMS in some of the trays. And then they had some background trays, and then they did their best to put the material back on. So it's a disturbed site. But the question was, if we do this, and we know we've got, we've loaded it up with ore, 1.5 meters deep, and then they came back in and they sampled it routinely. So this is a line, background samples, then the gold tray, more background samples, the VMS tray, more background samples, the background tray. They planted them in September 2007, took some samples and pretty much got nothing. A little bit noisy there for a little bit, but not much. And then finally in December 2009, a couple of years later, very different environment than many other places in the world. So it's not like this is going to be the same everywhere, but in Western Australia with that environment, it took a couple of years, and then there was a consistent response that's turning up at very low concentrations in the gold. Curiously, the gold actually behaved better than the zinc. I would have thought zinc would have nice mobility, gold maybe not so much, but zinc actually was not quite as consistent, but it turned up at about the same time, and a little bit less sensitive. So, I mean, there's a variety of possible mechanisms for transport of geochemical ions through cover. This is just one example that demonstrates that, yeah, it happens. Maybe we don't understand how or why. Some environments is probably focused a little bit more on water circulation. Some may be gases, some may be seismic activity, some may be redox related. And I think it does vary where you are in the world, but it's evident that it does seem to be happening in many environments. So this is a regolith sample, the photo on the upper left, and then it's a little bit of a mineral map. So you can see the scale there, it's 2,000 microns. And most of this material is a carbonate. And so you can see that there are little blebs of silica. That's the bright red here. You see these little blebs of silica, and that happens to be also where the gold is sitting, not in all of them, but in many of them. So if I analyze this whole sample, I'm probably going to get less than detection golds. But if I get rid of the carbonates and focus on the little blebs, I'm probably going to get a very interesting response that might be quite different from other samples. And the point of this is to say there are things that we can do to enrich either the grain size or the sample that we're working with. Because in many cases, 80% of the material we're working with is a dilution. We want to get rid of that and focus on where our metals of choice might want to be. So go back to Australia for a moment. Here's the red sandy desert. So when you pick this material up, it's sand. What color is sand usually? I go to the beach, it's usually white, right? Not always, but usually. But this is all red. So what is that red? And I think it's probably a highly charged oxide that's found its way on there. And so if that's highly charged, and what I really want is to analyze that, can I get rid of the sands so that I'm really analyzing where I think my metals may have lodged? So if we, so this is a part of what Newmont's done. Simon showed a picture like this in his talk at the SEG meeting, if you happen to have been at it. And so the idea is that you put the sample in with water, agitate it, disaggregate it to the best that you can. Then you give it a few minutes to sit. The coarse sand settles quite beautifully. I mean, our students do this all the time when they're looking at rock stability issues and soil programs. So the coarse sand settles pretty quickly, and then pretty soon we get to silt. We've got some organic in this case, which isn't the case in the Great Sandy Desert. And so what we have here is muddy water. And the muddy water then has particles that are very fine grained, generally less than 50 microns, probably less than 10. If we want true clay, we would want particles less than 2 microns. And so Bill had developed a method to get at that material without, instead of doing a wet sieve, get the material that you want up into a water solution and work with that. And so Owen started this out with a larger soil program, and the results were stellar. They were so consistent and beautiful. I thought, is this soil samples? This is unbelievable. So we started to do a little bit more work, and eventually that led to some larger programs. So these images have all been shown at PDAC and different investor conferences because Newmont used this technology to try to sell joint ventures for a period of time. And so these are just 3 examples. All of these are surveys of more than 1,000 or 2,000 samples at relatively close density. You can see the one image is labeled 35 by 150 meters, so very close spacing. And so we've paired a different size fraction with the best quality analytical care that we can have. Extremely vigilant QA QC, and in the early days we were rejecting a fair bit of data that came in, and you can see the results here. These are all districts that have known ore deposits in, and the game was to find more within the district. So this is kind of in a brownfield space, so you can see different scales at work here, but these are massive programs. They were all processed at the in-house Newmont lab, and that's a part of what they've been up to. So one of the projects was actually studied. Amira really set out to try to find this P778 program. I think they did over 100 orientations of soils and testing every analytical method and acacia trees and everything they could find, and did all these different orientations. And they never really arrived at the end of the project with the silver bullet on what we could do in that environment, not to mention other environments. So this is one of their soil surveys. You can see the conventional gold, what they call a conventional, probably minus 250 micron sample size. Here's an MMI response. Here's an arsenic response. It's a little bit there. And here's the MMI arsenic response. So, it was there. but not convincingly enough that they walked away and said, this is the method you want to do. We came in, and so this is what the ground looks like. It's flat as a pancake. These red sandy regolith. And so the scale's off a little bit. You'll have to look a little bit. You can see here the shape of the ore zone is this shape here. And so closely spaced samples with a uniform size fraction, again, that attention to detail on the analytical, and boom, you see that and you say, gee, we need to do something there. And so this is a nice little deposit that they're in the midst of working on. So that pairs into the opportunity to look again at isotopes. If we have a way to enhance the signature and look more closely, then is there more we can do, not with just the stable isotopes, but with trace element isotopes? And so I would not say this is a field that's arrived. This is a field that's exciting and interesting, and we have a lot yet to learn. But this is from Kurt Kaiser. He ran the Queen's University Isotope Lab for many years. It's a first-rate lab, and it's now being run by Matt Leyburn and Dan Layton Matthews. They're continuing to do some good work there. And so everything here that's in black, we can't do anything with, but the elements that are shown in yellow have 3 isotopes that we can work with, and those in red have 2. So what can we do with these? Can we push the detection limits down and give ourselves either prospectivity analyses or vectors that we can work with either in soils or in rocks? We do know that we're at very low concentrations with these. So it takes really good lab controls and excellent QA/QC. And sometimes even just getting a good reagent is a big challenge. It turns out from a lot of the work that's been done to date that redox reactions produce the greatest fractionation. So we have to either take that, the advantage of that, or be able to look beyond that. And so we have a lot of untested opportunity here. So this is actually pretty old. This is 2015. It doesn't feel that old, but Kurt was working with his students in Saskatchewan. This is Cigar Lake. And so you can see the number of faults in there, and they've picked up a nice response in the lead 207, 206 in the A, B, and C soils, and also picked it up in, let me see if I can move back up here. Oops, no. Okay. Also picked it up in the tree cores from black spruce, right in that same area. This is some more recent work with copper fractionation. This is from Ryan Mather's work, where he's looking to use fractionation from copper as a fingerprint for determining metal source. And in this case, he thinks that it has is a good reflection of the weathering of copper sulfides. So this is pairing a couple of things together. These are copper isotopes from water. So you've got to have very low detection limits to pick that up. And right there in the center, these are surface waters right in the pebble. Jeff Bigelow did some work with thallium at the Queen's Lab. And so these are mineral maps. On the top, we have a sample that does not have a particularly interesting thallium isotopic ratio. There's a picture of it. This is the scale. And in this case, you can see that the thallium looks like it's turning up where the potassium is, and it's not correlated with sulfur. So that sample's got thallium sitting in feldspars or clays. There's this sample, which has an interesting thallium isotopic signature. Not a lot of contrast, as you can see. Here, the thallium is turning out to be where the sulfur is. So we have thallium occurring in 2 different places in this sample. So the question then, what begs the question is, you know, we would get a surface map with a thallium on it, and we might see some thallium and drill it and come up with some gold and be excited about it. And other projects where we might get what we would call a false anomaly. Well, maybe that's the thallium related to a different source. So is it possible that the isotopic ratio would help us sort out different types of anomalies and help us know which ones are more prospective? And so this is this is early stage work. Jeff just presented this in a poster at PDAC. I don't think there's more work happening on this just yet. So I'm just juicing you with the possibilities. But this is a cross section with some samples from the core, where you see the golds on the right, the complete the total thallium general analysis here, and the isotopic response. So reasonable ranges for all of these. The gold's up to 50 ppm. This is right on top of ore, and in this case, thallium appears to be a proxy for oxidation. But there's some possibilities that if we can retain the signature from a deposit and retain that isotopic signature in soils at the surface, that we might have something new to work with there. So just whet your appetite on those. I don't have a lot of answers for that, but it's why I call it this a renaissance period, where we're seeing some indications that if we keep working at it, we're going to find some new approaches. So mineral chemistry, mineral mapping, I mean, this is a major research area in economic geology. The SEG meeting that was here last year, there were talks about zircon, tourmaline, pyrite, calcite, apatite, magnetite, monazite. I mean, there were a lot of talks about mineral chemistry at that meeting. The Geochem meeting, applied geochemists meeting in Chile. There were also talks about mineral chemistry of various minerals. And Joshan here in the department focuses on this, as do several other research organizations. And it is now possible to get good mineral chemistry work done at commercial labs. And so this is now a viable approach if you've got the right application. So we can do some mineral sampling techniques, chemical characterization, mineral mapping, look for indications of mineralization, vectors, isotopic analysis, and of course, age dating. So our old style heavy liquids separations, sieving, shaker, this is all still completely current for samples that have been disaggregated. And then we can take those grains or rock samples and push them into the automated mineralogy now. So this is where we've changed to the ability to identify rare minerals and quantify all of this to a great degree. And so this quantitative data gives us a whole new tool set with those. The electrical pulse disaggregation allows us to take a rock sample and kind of turn it into a till or sediment sample. So there's one of these at the USGS now here in town, and there's a few of them around. There's one available commercially at Overburden Drilling. And in this case, the rock sample, instead of trying to crush it, which has never been successful in coming up with mineral grains, you can take a ½ kilo sample, select it to an incredible electrical charge, electrical volt that's sitting in water, and it just breaks the sample apart along the mineral boundaries. And so you then have a broken up sample. You have clay in the water, so you can take the clay and do what you like to with it off of a hand sample. And then we've broken that down. So some of the analytical methods around mineralogy suffer from sample representativity, where you only might pick up a few grains, and then you make a lot of assumptions as to whether those represent the rest of the sample. And this allows you to pick up a whole bunch. So this is a sample, well, gold obviously was in the sample, and those are all the grains that came from a hand sample. So we can look at it, we can see the grain sizes, we can see, is it pristine or rounded grains? So this is one of my favorite ways when I'm wanting to have a look at a rock sample and get more of a feel for what's in it. And I reckon that if someone had visited Busan and brought home just a hand sample with permission and had sent it in, they might have seen that instead of seeing what should be grains looking like an epithermal system, that they would have seen nice little rounded grains. So it's actually quite handy for forensic work as well. So these are pictures from Beth McClenaghan, who has continued to run a very effective programs looking at indicator minerals around different systems across Canada. She's with the Geological Survey of Canada, and she's looked at all kinds of systems now. And so we're now moving from, okay, we know that we've got interesting grains, the diamond story is well known and well established. We've got other systems that we can now characterize. And so we can now move these to not just the color, the shape, the presence, but also the chemistry of those. So the first chart here, this is actually some pretty old work, but these are the rare earths. So these are background samples here, and these samples here are from the Kalamazoo copper porphyry, and they've got a lot of rare earths in them compared to the others. And so from a prospectivity standpoint, that might be an interesting thing to look for in apatite. And here we have samples, rock samples that have come from the different alteration systems of that same system. And you can see from the box plot that there's a nice segregation. So when you move into the deposit, opportunity to perhaps vector to figure out where you are. Now, this is some newer work, was published fairly recently, looking at tourmaline and porphyries. So you can see that the different, they looked at 7 mineralized porphyry deposits, and these box plots show the difference in concentrations for a couple of elements. So you can see that, there's some segregation. Just put it into this ternary diagram, and so the samples that are related to porphyry coppers are falling in this zone here with the red dots. The orogenic golds tourmalines are falling over here, and the granitic pegmatite tourmalines are falling down here. Metamorphic tourmalines are also characterized. So we have a long ways to go to understand some of these systems, but applying chemistry to what we've been doing in the past around presence or absence of minerals is giving us great opportunity. So also around the chemistry of systems, then when we start looking at the shortwave infrared, there's a lot of different things you can do with that, the field portable instruments, different types of scanners that are out there. And we're looking not just at the presence of some of the minerals, but also the chemistry of those, and they reflect differently according to their chemistry, particularly the micas and chlorite, but also the carbonates. So this is another study that was presented at the SEG by Adu Agyapong from Ghana. And it's just unfortunate the way the conference fell, and perhaps he didn't have enough name recognition. There were only about 10 people in the audience for him. I was sort of heartbroken, honestly. This is a beautiful bit of work, and he presented it very nicely. So in the past, the Ahafo system in Ghana was reputed to be impossible to model. They had gone back through the core and relogged it 6 times. The alteration was cryptic, and at the end of the day, they were using gold grade to create the models for mining. And it's a big district, millions and millions of ounces of gold have come out of it. And the geologists had kind of thrown their hands up. Different small studies had been done, but we were able to get in there one year that had a bunch of extra money. And we were able to talk them into doing a lithogeochem and core scanning study. And this is the outcome of it that Adi presented. And so this is the golds starting at 250 meters down to 650 meters. This is an angle hole back against the footwall faults, and the gold's sitting down in here. And they've been able to identify 5 alteration zones with this scanning. The core pieces are just sitting next to each other, and this is not continuous scanning down the hole. This is one type sample from each core box. So it's a little bit of a squeezed section, as it were. But the first thing that happens as you begin to get closer to the ore zone is that amphibole disappears, which makes a lot of sense. The chlorite begins to change composition, which is what we see with the changes in color here. We begin to pick up white mica. We also begin to get iron carbonate. And the carbonate story is quite a nice one. We move from pretty clean calcite out here through a magnesium switch into an almost siderite composition. And you can actually almost model this with the carbonate. Then there's actually an aluminum mica that turns up that we didn't even know was there. And they shouldn't be able to pick up silicates with this, but they were picking something up that looked unusual to them, and they called it jasper. So now we go from thinking that we had no alteration, or maybe 2 meters at the most around this orogenic gold system, to having a pretty easy 50 meters to tell us that we're getting close. And if we can pick this marker up as well, then we're well out 100 to 200 meters away from the ore zone with this approach. So that's visual, that's all well and good, but they'll quantify that for you. So here's the quantified data, which you can then put into a model, and they can use this for modeling the deposit. So they took this deposit, happens to be extremely well behaved. And they took all the holes of the deposit and squeezed them onto a cross section against all the rules, right? But look how well it's behaved. So this is using that model that I showed you. This is the probability of being within 25 meters of ore modeled here. So there's a fault here, the ore zone sitting right in here, and you can see that the whole deposit squeezed into one section, which we shouldn't be able to do, is actually giving you a very nice response. It turns out that you can also model that alteration with a complete lithogeochem package using some of the lithogeochemistry and alteration tools. So this is just geochem data of the same thing. A lot slower to get, a lot more expensive, but similar response. So the tools that we can start to bring to bear then come out of the IOGAS software. It's really become the software of choice for geochemists, and it's particularly strong in the lithogeochemistry modeling capabilities. So, 15 years ago or before, you'd have to make up your own little graphs and go get some industry data and put it in there, and they've pulled all that together and given you type samples of a whole series of graphs, and all you do is load your data, and bingo, you've got a lot of discrimination capabilities, molar element ratios, Pierce element ratios. And Scott Haley in Australia has given a lot of short courses, really promoted the potential for using lithogeochem data and some of what you can do with it. He's probably been more verbal around it than most, and so there's a tremendous tool there. The other nice piece of software that was put together came out of CSIRO. June Hill, this now 2017, so it's been around for a little while. But she was challenged with the fact that we can look at multi-element data, but even if it's on a downhole survey plot, we don't have a good way to statistically cluster downhole information. So we're still kind of manually having to look at the downhole aspect. So she worked on a clustering routine. It's a data mosaic where proximity of one sample to the next was also part of the clustering evaluation of multi-element data. And this is actually quite powerful for downhole data. And they liked it well enough that this has actually now been put into IOGAS as well. And you can pick how broadly you want to create these clusters, or how loosely they have. You can use the CSIRO software right off of their website, or you can pull it out of IOGAS. So all of these sorts of things in the brownfield space lead you to thinking about our logging systems. We log the core, we mark the core, we spend a lot of time with it, we learn a lot about it. We may or may not have an opportunity to get more SWIR data, perhaps some scanning XRF data like the MinAnalyze. Maybe we've collected some ecotip hardness measurements. If that all comes together for the geologist right in the core set, when the core is still spread out, he has the ability to go back and look at that core again. Whoops, did I get that wrong? Hold on, this is saying this, is that right? And so the ability to iteratively evaluate the core really comes alive. And so I think there's an opportunity to pull all of these new data together more quickly in an iterative fashion and allow you to interpret your data and then reanalyze it, get it into Leapfrog, test the models, and give the geologist more tools right at the front end. When you get onto some of these big projects out of a point of necessity, and I understand how it happens, you've got 50 loggers, you might have 3 or 4 people that are putting cross sections together, and you got one modeler who's back in head office. And so you get this big separation from the rock to the interpretation. And so this is actually one of my dreams, is to pull together a smart logging system that squeezes all of that down so that the logging geologist is much more involved in the final interpretation. So that sort of pushes us into this discussion of what I would like to call guided machine learning. Machine learning blank with no information, I'm not so excited about, but I do like the idea of guided machine learning, which means that you do a lot of iterations with your geology hat on and have a look at the outcomes and make some sensible responses out of it. But if you've got a project with 66 geochemical elements, complete characterization, maybe 14 or more mineralogical parameters, it gets past what you can do as the smartest person in the room to manage all that data and really get everything out of it. And our multivariate methods that we've used in the past, like cluster, principal components, factor, discriminant, they're very powerful, but they don't take advantage of any kind of spatial relationship. So my outcome from that always has to come back to the map, and I'm trying to sort, you know, I almost personally think it's worse in ArcView, where you've got layers you're turning on and off, and it gets very difficult to really see the value in it. You can't see zonation. And so machine learning and some of the potential behind it allows us to put spatial context in as one of the base parameters. So instead of making spatial context the last thing we think about, we actually put it in as one of the first things. And then we, put our hats on, pull the geophysics in, the geochem, anything else that we can pull out of it. And I guess one of the great things about this is if you've set it up right, you can do this iteratively. Every time you have new information, you iterate the process. This is new space with plenty of opportunity to defend yourself. And I think, we're probably going to experience some disasters in the industry and some really interesting work. But it's quite telling that, Goldspot was one of the companies that was really out there excelling in machine learning. And working on it. There's a couple other good firms in Vancouver that are also doing similar work. And Goldspot was bought by ALS Minerals, the lab group. So they're seeing the opportunity to push into that space and bought out one of the, what I think is probably one of the better organizations out there for it. So just a little bit of a challenge for you. I've thrown some unusual ideas, maybe some different concepts, a little bit of forward looking around, geochemical renaissance doesn't mean that we're looking back. It means we're pressing forward into new opportunities. And I hope I've given you a little challenge around some new opportunities, some that you might like, some that you're really not so sure about. But this is a standard innovation curve. Everyone in the IT and oil and gas industry is well aware of it. Of the population in most of the world's most fields, there are innovators that are 2.5% of us, and there are visionaries that are early adopters. And then there's this chasm, this gap. And then there are the pragmatists. It's probably a lot of geologists, conservatives, and then the outright skeptics that are sitting at the back of the room going, oh yeah, machine learning, give me a break. So most ideas are not by definition accepted at first, and it takes some big steps to get across that chasm. So this is not just in geology. This is, you can find this on the web. This is years since invention, 2% adoption rate. So the mobile phone took almost 15 years from inception to being well adopted. You can see that this is somewhat of an older graph because here's video calling was only at 19% after 85 years from when it was first available. It took COVID for us to get up to, what are we, probably over 90% now. And you can see other ones, but there's nothing that's managed to get, to a wide adoption after 15 years. So we put that cycle on top of our business cycle when there's a lot of times we don't have money, and it's no wonder our industry really has a hard time moving forward with innovation. We've had series of 4 or 5 cycles over this 100-year time period, and when we're at the top of the cycle, as most of you know, you got more money than you know what to do with. There's pressure, 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 go, go, go. You don't really have time to think. When you're at the bottom, you've just laid off half your staff. Everyone's depressed. You don't have any money to do anything. And so it turns out that it's the rising part of the curve where that's sort of the innovation opportunity. And it's a window that doesn't happen very often. So you kind of have to feel for the vendors that are trying to put out a new innovation right here. Because they kind of have to wait for the industry to be able to pick up as well. So this is a real challenge for us, I think, in mineral exploration, between the natural tendency not to pick up innovation and the business cycles that are a part of our business. Minex Consulting put out this article that suggests there were 72 innovations in this time period, and an average of 10 to 15 years for wide adoption. So it sort of speaks to why there's really no point in keeping big secrets to yourself, because even if you published it, like, you know, there were several really, really good bits of information that came out at SEG 2022. It'll be 10 years before most people have gotten on board if it follows the statistics. And Bill Coker used to say that. He said, we'll just talk about what we do because most people won't even realize what it is that we've just said. So exploration in the next decades. Yeah, I'm coming up on time here. I think, you know, we do have a lot of opportunity. There's a lot of good data out there. There's some just exceptional research going on at different institutions around the world, and the commercial labs are adopting a lot of it. They might take a few years, but they are coming along, picking up the new instruments and providing new data. And we can apply these anywhere from the greenfields to district scale. You know, our exploration continues to be more complex, deeper ores, search and covered terrains. There's nothing new to you about that, but I think we're continuing to find value and the opportunity for discovery success with some of these new approaches. Thank you.
Thank you, Mary. That was great. I didn't know they were doing things with isotopes already.
Oh, yeah, a little bit.
Neat. Questions? I'm sure there's a few.
Yeah, just a simple one.